in today. We started recording. So what we're going to let's see if this works. Yeah, it works. What we're going to cover today is some topics I've been working on for like the last few years. One about the past, like what happens with sea level over the past century, and how we can improve our understanding of what happened over the 20th century with sea level. Then we jump to the present, where we're seeing some sort of a little mismatch that appears in observed sea level versus what we expect from melting ice and thermal expansion. And finally, we going to look into the future, and not like with long-term projections, but see whether we can make sea level predictions on more like seasonal timescales, whether we can like predict sea level a few months ahead of time. But before we go into this topic, I just want to give like a very short sea level 101, so that we're all at the same level with some of the terminology that I use throughout this talk. So let's go to sea level 101. This picture is, some of you might remember this from their undergraduate school textbooks. It is a picture of all the heat fluxes in the Earth system, right? There's like heat, shortwave heat coming from the sun. Part reflects, part gets absorbed by the Earth, which emits it back as long wave radiation with all sorts of feedback in between. But these are all pretty big numbers, all like in watts per square meters. But there's like one small number in the lower left on this picture. That's like the net absorbed heat, and that is the amount of heat that accumulates into the Earth system, and it's that's the heat that causes the planet to warm, and the number is said like much smaller than all the other fluxes in this picture. But if you integrate it over the whole Earth surface, you get this number here per year, and it should be 22 zeros. I hope I counted right when I typed all the zeros, and that's the 10 zettajoule per year. That's more or less every year is accumulating in the Earth system. But where does all this heat go? Because that's important to understand for sea level. And this is an estimate of the total. In this graph, you see like the total heat accumulation over the last 50 years, estimated from by Carina von Zoekman and colleagues last year. And you can see that it's rising, that over the last 50 years, the Earth has accumulated more than 300 zettajoules. And only a very small fraction of that is actually going into the atmosphere, causing like the surface temperatures to change. And there's also like a small fraction that heats the soil. And there's a fraction, of course, that causes land ice and sea ice to melt, like it's like latent heat. And when the ice that melts is on land, it generally flows into the sea and causes what we call barystatic sea level rise. That sea level rise because we add extra mass to the oceans. But the most of the heat is absorbed by the oceans, and the oceans warm as a response of the heat they absorb. And because what gets warmer will expand, and the same goes to the ocean. And the sea level rise, due to this thermal expansion of the ocean, we call that thermospheric sea level rise. And like both barystatic and thermospheric sea level rise are the main drivers of global sea level rise over the past and also into the future. So the nice thing about this graph is that you can immediately see that the two processes, like the number 1 and number 3, in the Earth heat accumulation, are immediately driving sea level rise. So it's really a very direct consequence of the fact that heat is accumulating into the Earth systems, that sea level is rising. So how does a sea level rise look like that's caused by this process? So it's that like sea level rise is the result of multiple processes. We just discussed like the barystatic sea level rise, global mean sea level rise, because we add extra mass to the ocean. And here on the right, you can see some estimates we made last year for a project to look into like, do we understand like the drivers of 20th century sea level rise, and how does it compare to the observations? So this is like an assessment of multiple observational sources to put a number on like the amount of sea level rise due to all these terms. And here you can see that over like the 20th century, glaciers and Greenland have caused the majority of very static sea level rise. While Antarctica has been like slower, but like over the last years, we see that Antarctica is quickly catching up. And there's also, next to melting ice, there's also an exchange of like liquid water between the continents and the oceans. Think about groundwater changes, think about lake levels. And that has caused actually probably a small sea level drop over the 20th century. And that's because as humans, we built a lot of dams. And when you build a dam, you create another artificial reservoir, and that removes water from the water side. So that causes a sea level drop. Although we don't really build a lot of dams anymore of like the last 10, 20 years, and we're pumping up more and more groundwater. So actually this trend has slightly reversed over the last few decades. And then, of course, we have thermospheric sea level rise here. That's the last line I just plotted. That's in the same order as the glacier contribution over the 20th century. But what you can see from this plot here is that there is not just one dominant process that drives sea level rise. It's more partitioned among like multiple processes that happen on like more or less the same order of magnitude. So if we add all these processes, and that's the blue line, you see that it's like much larger. That's not just one component that dominates it. But the nice thing that this blue line agrees pretty well with the observed 20th century sea level rise. We have observed that from tide gauges, and since 1993 we can also measure it from space with satellite altimetry. And what you can see here, and that's something you can clearly see in both in the observations and in the estimates of the process, that sea level rise is now going faster and faster. Right? We've seen 20 centimeters of sea level rise since 1900. Of which almost half happened only after 1990s. This pace is clearly accelerating, and this acceleration is also not driven by one dominant process. We can clearly see that the thermospheric expansion is clearly going faster and faster, and now also over the last few decades, the ice sheets are also increasing their speed, which they cause sea level rise. But this picture is actually a very simplification, and we talked about global mean number. So if you look into what satellite altimetry tells us about like the spatial patterns of sea level rise, so that's what you see here. This is the trend in sea level since 1993. This global mean number is only a mean of something that differs a lot from place to place. For example, here in this picture, look to the US, you can see that satellite altimetry shows that sea level on the east coast in the Gulf of Mexico has risen much faster than here on the west coast. So when you hear, for example, in the news, maybe you've heard it like that. Last week there were a lot of floods on the east coast, while you hear these stories much less from the west coast, and that's basically because sea level on the west coast is just not rising as fast as on the east coast. So that's where you see the problems first. And the cause of of this picture is not one process. There are changes in winds that drive sea level changes. There are changes in the ocean currents. There's change in the temperature of the oceans are not rising uniformly. There's change in salinity. There's all sorts of processes behind this. But there's another very important process that altimetry does not see, and that is the fact that when we're on land, the land itself, where we are on, can also move upward and downward. And then we can talk about what's called like relative sea level. And that is sea level changes relative to the land we're standing on. And that's the thing that we measure with tide gauges, for which we have a lot of long-term records. So here on the right, you can see how that looks like in practice. Here's like 4 tide gauge records from the US, like on San Diego, it's close here, Seattle, New York City, and Galveston, that's close to Houston in Texas. And you can see, for example, that sea level in New York City and Galveston has risen much faster than here on the West Coast. So what we saw in satellite altimetry, where you see like these big regional differences, these differences can persist on very long time scales. But in the case where you can see, like, for example, here in Galveston, that showed like by far the fastest rate of sea level rise. That's mostly driven by coastal subsidence, but the fact that Galveston is literally sinking, and therefore relative sea level goes quickly upwards. One of the processes that's behind all these regional patterns, especially with relative sea level rise, is what we call so-called sea level fingerprints. And that means that if when ice sheets, for example, lose mass, they start deforming the Earth, right? So we have like a lot of ice that pushes on the solid Earth below, and when we remove that ice, the solid Earth will bounce back. So the Earth will deform close to the ice sheet. The land will lift up, and far away, then the water goes from the ice into the ocean. So the ocean gets heavier and subsides. And that means that sea level rise will be much slower close to the melting ice sheet than it's far away. And that's something you can see here in this picture. Here you can see like the sea level rise when Greenland loses 1 millimeter of global mean sea level rise a year. And you see here the regional effects of that effect. So you see that close to Greenland, sea level will actually drop, while far away it will go up much faster. And this is a tricky thing, because what you can see is that, you know, remember from the previous picture that over the 20th century, sea level was mostly caused by what happened to Greenland and glaciers, and they give, like, especially here for the US, like a below average sea level rise. But for the 21st century, we think that Antarctica is going to play a big role, and then this whole figure is flipped around. Then the US will get more than the global mean. So this is like, because we shift partitioning of sea level rise, also the regional patterns of sea level rise will change. And there's also like another effect of this is that you can see here that we move a lot of water from the polar regions towards the equator. And what that means is that the Earth will also rotate slightly slower. So due to climate change, we will also make our days slightly longer, although that's probably not the thing we should worry about most, but it's like a fun fact you can share with all your colleagues if you need it for a fun fact. And the thing that I often do is like look into all these processes, try to understand regional sea level, try to understand like what are the typical drivers for sea level at a local place, and see whether we can add them up to the observations. Because if we know all these local processes, we know what causes the local subsidence, we know what's causing these spatial patterns, we can make we can use that knowledge to make improved predictions to what happens for the next century, so people can prepare for that. So with this quick introduction of sea level, let's now move to more of the new stuff. And first we start with sea level changes in the South Atlantic. So this is something I've done with a group of people over the last 2 years, where we looked into sea level in the South Atlantic and see what the observations tell us about what happens here. So the question is, why are we interested in the South Atlantic per se? And that is something you hopefully can see from this figure. So this figure here shows all the tide gauge records that we have. And tide gauges are like our main source of information of sea level changes before we had satellites. And every dot is a tide gauge, and the bigger the dot, the longer the tide gauge record. And you see some colors. This is here I separated the ocean into six regions, and in each of these regions, sea level behaves more or less coherently. So we have some sort of 6 more or less coherently moving regions. And here on the right, you see the number of tide gauge records we have for each year. And you can see here, especially like in the northern hemisphere, in the US, in Europe, we have a lot of long records. In Asia, we have some in Australia. But here in the South Atlantic region, you can see that we have very few records. And even if you go back into time, like before the 1950s, we generally only have like 1 or 2 long records. And that is a problem, because we have this very large region in the ocean where we have very few records. So it gives a lot of uncertainty, both in like understanding what happens to global mean sea level, because like a large part of the sea is engaged, but also like for regional sea level, like how does the South Atlantic behave compared to the other regions? That's really difficult to constrain, because we just don't know what exactly happens here. So what can we do to solve this problem? And we came up with 3 things that we could try. The first thing is like, can we find another more tide gauge observations? And so these tide gauge observations, many of them, they were early 20th century. They were recorded on paper, they are recorded in notebooks, and many of them, they are stored in archives where we actually have no clue of them, and they're undigitized. They're not in centralized databases. So there might be much more information on sea level available than we currently know. And the second thing we want to try is see whether there are other ways of getting ideas of sea level changes by looking into, instead of tide gauges, to like direct measurements, to paleo proxies, and see whether they can tell anything on 20th century sea level. And finally, we also want to have a look, like we have some ideas of the spatial sea level patterns. So can we say that, for example, a specific tide gauge will under or overestimate sea level rise in the South Atlantic? So we're going to try these three things. So this is again a map, and the first thing is of the South Atlantic, and the first thing I want to have a look at is in Dakar. Dakar is the capital of Senegal in Western Africa. And what happened is that Senegal used to be colonized by the French, and some colleagues, they found in an old French archive, they found a lot of old rolls with tide gauge observations from Dakar, and they digitized these records. And one thing that you have to know, if you measure sea level with a tide gauge, especially when you have like multiple instruments, what's important is that you have a benchmark that you can say, like sea level, the height of sea level relative to a stable benchmark, for example, a rock or a geodetic marker. But luckily, they found information on these benchmarks in this archive. So a group of people, they went to Dakar, and they found all this old benchmark information. Now you can see here's like an old benchmark in a ditch in the street, and there are also like some old buildings that have these benchmark locations. And there's also like a tide gauge that actively measures sea level right now in Dakar, and it was also benchmarked. So they reconstructed all this benchmark data so they could link the old records to the current records, and that was able. And with that, they were able to make this nice new sea level curve, where you have like multiple tide gauge information. This is like a tide gauge, this is another tide gauge, and this is like the modern record, but they're all referred to the same height level. So this is very accurate. Although it's gappy, the measurement itself should be very accurate. And what it does, what it nicely shows, is that it's again another independent confirmation that sea level has risen over the 20th century, and this showed the trend of about 1.3 millimeters per year. That's pretty close to the global mean. And what also is, I think, as far as I know, this is the longest instrumental sea level record from Africa. Yeah, thank you. Yeah, from sea level from Africa. So that is already like one extra dot on the map. And then for the other thing, we looked into a salt marsh reconstruction in the Falklands Islands at the other side of the basin. So we moved here from Dakar now to the Falklands. And how does that look like? And here you see a picture of a salt marsh. And paleo proxies, they're often used to estimate sea level change on much longer timescales than 20th century, as people use that to like make reconstructions of Holocene sea levels, but even like over multiple millions of years. And but often like the spatial and temporal resolution of them is often not high enough to say something on the small sea level changes we see over the 20th century. But salt marshes, they sometimes form an exception. So what is a salt marsh? Is like a place that is occasionally floods, and because of that, there's like a lot of microfossils that build up. So by digging up the mud and dating the microfossils you find in there, and for example, you know that the specific fossil lives at the high tide line, you can reconstruct the high tide line in the past. And sometimes they have a lot of good microfossils in them, so they can provide very detailed information, even on century scale changes. And this is one of these examples where we are very lucky that we got a lot of high quality index points. So this was dug somewhere in 5 years ago by it's like the whole PhD thesis of Thomas Newton, which did together with Tim Daly and Roland Garros. So they went there, dug up the mud, and they came up with this reconstruction of salt marsh reconstruction. So every blue dot is a sea level index point, and this goes back like 1200 years. And you can see like a slow rise and then flat, and then this very steep rise somewhere since the 1850s. And as a nice independent check on this data, there was an English explorer, James Clark Ross, who went to the Falkland Islands in 1850 and measured sea level for a week. And he also put a benchmark. He just punched a nail in a rock, and he measured sea level relative to this nail in this rock. This nail is still there, so we still know like how high sea level was when this explorer went there. You see this red dot. It's slightly higher than the rest, but actually it matches up pretty reasonably well. But what's interesting here is like the number of records after 1900. You can see that there are like 15 or so index points, and that is enough to say something about to have another constraint on sea level rise here in the South Atlantic. So this is very lucky. It's a very high quality record, so we can really use it as a low pass filtered tide gauge almost. So then we have these two new records, and then we have to say like, what do these records tell us about sea level rise in the South Atlantic as a whole? And so remember from this from the previous slides that sea level varies a lot from place to place. So if we have only very limited records, we don't want to bias our estimates, but we can make some guesses. For example, here on the right, you see an estimate of these the sea level fingerprints from 1900 to 2018. And you can see, for example, that here in South Africa, you'd expect more than average sea level rise. Well, here in close to Argentina, you would expect slightly less. So if you know that information, you can correct your estimates. And the same goes for glacial isostatic adjustment. The Earth is still deforming after the since the last deglaciation. It's called glacial isostatic adjustment, and that also has a considerable effect of sea level. And finally, and something that has been emerging over the last few years, is that more and more tide gauges, they are equipped with permanent GPS stations, which measure vertical land motion, so we can also assess the stability, the vertical stability of the tide gauges. So here's an example of someone installing a GPS on a tide gauge record. So with all these three tools, we can start estimating what happens in the South Atlantic as a whole. So here you see like the records that we now have. So we have like here are some existing tide gauge records. Here's the new Dakar record here, and here's the new Falklands salt marsh record. And here you see in blue, you see the trend over the 20th century, just from the measurements themselves. And then we can start making estimates of what happens in the South Atlantic as a whole based on these spatial biases. So if we correct for glacial isostatic adjustment, we can correct for sea level fingerprints in red, and then we can also correct for vertical land motion that we measure with GPS, and we can combine all these corrections with this in green. And what's interesting here is that for most stations, the blue bar, the green bar is slightly above the global mean. Global mean, I think, is from 1900 to 2010, is like 1.2 millimeters per year of this period. So most of them, they are above that. But if you look, for example, in Buenos Aires, which was generally like the only record used in many sea level reconstructions, you see that Buenos Aires has a trend of 2.5 millimeters per year over the 20th century after all these corrections, which is certainly higher than for the others. So it might be by just relying on the Buenos Aires record, you might overestimate 20th century sea level rise in the South Atlantic. But just by having more records, you can really see that like they are uncertain. So by adding more of them, we should get a more accurate estimate. And that is what we tried here. So here we try to reconstruct sea level in the South Atlantic as a whole, and then it's still very uncertain. This is like a PDF, so it's like an uncertainty distribution, and then blue is without any corrections, and green we start correcting for all these local protections. So it seems like despite that the uncertainties are high, and these vertical lines are global mean sea level estimates of sea level trends of 1901 to 2010. And you can see that the green curve is generally to the right of the mostly global mean curve, which suggests that sea level in the South Atlantic has risen slightly faster than the global mean. But it actually makes sense, because we know that the Atlantic Ocean is warming at an above average rate. So there's like more heat accumulating into the Atlantic Ocean, which is not fully offset by salinity. And because the South Atlantic is far away from most glaciers and ice sheets that have driven sea level rise of the 20th century, we also expect an above average sea level rise here. So you can see here that this number does make sense, right? We measure a slightly above global sea level rise here, and that also matches with the processes that we expect. So you can really see here that by all this data rescue that is still going on, and paleo data can really help us to understand these regional projections, and we can start filling in these unknowns in the global sea level map. So this is all about the past. Let's go to the present, where we do have a lot of measurements, especially measurements from space, but that doesn't really solve all our problems, as we will see here. This is something we published a few months ago on the Earth energy imbalance measured from sea level observations. And the central term here is what we call the sea level budget. And what we mean with sea level budget is basically where we compare like observed sea level with the barystatic and the thermospheric component, because they should add up to the total. And we're currently in what's sometimes called the golden age of sea level observations, where we directly measure all the components. And we measure total sea level rise here from with satellite altimetry. Like a few months ago, Sentinel-6 is Mike Frederikse is the last satellite in a series of satellite altimeters that measure sea level rise. And we also have measurements of barystatic sea level rise from the GRACE and GRACE follow-on satellites that map the gravity field, the time variable gravity field of the Earth, from which we can deduce how mass is moving around over the Earth's surface. And finally, we have the Argo float network. That's not fully from space. That are floats with a thermometer and a conductivity meter and a pressure meter on board that float freely to the ocean. They go to depth, measure temperature and salinity on their way down and up, and then transmit their measurements back to land. And from these temperature changes, we can deduce thermospheric sea level change, because we know how sea level density of water changes when the temperature changes. And the only component that we do not measure, or not measure very well, is what happens in the deep ocean below 2,000 meters, and especially like the temperature and salinity changes over there, because Argo floats, most of them, they only go to 2,000 meters. But the first initial thought that we had with this reconstruction is, then can we estimate deep ocean thermal expansion and deep ocean heat uptake by this budget approach, right? If you take total sea level rise, you subtract barystatic sea level rise, you should get thermospheric sea level rise over the full ocean depth. And if you then know what happens in the upper 2,000 meters, the residual should be happen in the deep ocean. But that didn't really work out, as I will show here. So here you see the recent numbers that we got from this study. This is all from 2005 to 2019. So we have in black, we have global mean sea level rise from altimetry, which is now rising by about 4.1 millimeter per year since 2005. And then we have barystatic sea level rise due to the melting ice sheets, the added mass to the ocean, it's about 2.4 millimeters per year. And we have thermospheric expansion measured by Argo of 1.2. And you can already see that if you add it up, we have a residual of 0.5 millimeters per year, which, and you maybe see it from this graph, that's mostly happens for the last 5-6 years of this record. And if you're naive, you'd say, okay, this might be deep ocean heat uptake, because that's the only thing we don't measure. But we have some measurements of the deep ocean, mostly by ships, by research vessels that uses CTD measurements that go all the way to the bottom. And our best estimate is actually an order of magnitude smaller than this residual here. So this is from a study from Perky and Johnson, who estimated that it should be like more in the order of 0.1 millimeters per year, much smaller than 0.5. And there's another argument you can make, like the ocean is very slow to react to sea level change. So to get all this temperature changes to the deep ocean, we wouldn't know like a process that would cause so much deep ocean thermospheric expansion. So this 0.5 number seems to be on the large side. It suggests that there might be something else going on here, and you can see that you can see it in a way that we might have a mismatch in thermospheric expansion, and because like ocean mass has the nice property that ocean mass should be balanced against land mass, and we have like a lot of independent measurements to know what happens with the ice sheets, what happens with the glaciers, and that all adds up pretty well. So it would be very weird if this residual would be caused by changes in errors in the GRACE satellite. So what we then end up with is two estimates of steric sea level. One that we have like from the upper ocean from Argo, and one from the full column steric sea level from altimetry minus GRACE, so total sea level minus ocean mass. And this difference again is like much bigger than what we expect from what happens in the deep ocean. And this becomes more problematic if we use this steric estimate to estimate changes in the ocean heat content. I remember that from one first slides that ocean heat content, ocean heat is like the big basin that absorbs all the Earth energy imbalance heat. So all the heat of due to climate change that accumulates in the Earth system. Virtually all of it ends up in the ocean, and ocean subsurface temperatures are actually the only way that we know to keep track of this Earth energy imbalance. We don't have like another measurement system yet to really measure that. So these ocean subsurface temperature changes are like very pivotal in constraining this number. But now we get a different number for the ocean heat content based on this approach that shows like a larger increase in ocean heat content. So that might mean if we assess this mismatch as a problem with the hydrographic observations, that's not the only option, but it's one possibility. That might mean that the Earth energy imbalance is actually slightly larger than what we currently estimate from Argo observations. And now, of course, the question like which number is more accurate. So to add a bit to this this puzzle of like what this difference of ocean heat content, we went again back to space, where we have observations of the ingoing and outgoing fluxes at the top of the atmosphere. So the heat fluxes, like the long wave and short wave heat flux at the top of the atmosphere, they are measured by the Ceres mission. And the Ceres mission, as from like you cannot really estimate like the mean radiative imbalance, but you can estimate like the year-to-year variability very accurately. At least that's what we think. So then we can start making a correlation of like the annual ocean heat uptake versus the annual top of atmosphere radiation flux, and that is what's shown here. So here we have again our two estimates. In orange is our estimate from Argo, from hydrographic observations, and in green is our new estimate of altimetry minus GRACE, and in blue is the top of the atmosphere. And the fun thing what you can see is that both Argo and altimetry minus GRACE, they show much more year-to-year variability than what Ceres measures, but the correlation is strikingly different. While hydrography does not really correlate very well with the top atmosphere energy flux, our GRACE estimate does with 0.8, which is very high. But again, the variability, the size of the standard error, standard deviation, it just doesn't match up with. It correlates very well. So this is a bit of an enigmatic situation. We still don't really know what to make from this, but it's still something we don't have a grasp on. And the puzzle can even get more complicated. Is that we look like where in the ocean does this thing go wrong? So we have like all these measurements. They have like a spatial map. So here we start with geocentric sea level from satellite altimetry. Then we have to apply some corrections for the fact that the ocean of the solid Earth is deforming, and then we have global mean relative sea level, and this global mean relative sea level has part of like ocean mass, which you measure from GRACE, and that already shows something very interesting is that here in the Indian Ocean, ocean mass is rising slower than in many other ocean basins, and we still don't have like a good ocean dynamic or like a solid Earth explanation of why this would happen. This is some sort of signal that we don't really understand. And here in the upper ocean, this is the upper ocean. This is the upper ocean steric sea level from Argo, and this is our full column steric estimates by subtracting ocean mass from relative sea level. You see these pictures look pretty much like each other, although this one has a more pronounced spatial pattern. And this is the residual, right? It is total sea level, which you measure from altimetry, minus ocean mass, minus hydrography. And this, if everything would work perfectly, this should be deep steric expansion. But you can see that there's very large trends. Look at this map. We're talking about multiple millimeters per year, which is way off what we think what happens in the deep ocean. And you can see that this place of this below average ocean mass rate is showing up here as a place of positive residual. But if you, for example, look into the Pacific Ocean, you might see that the residual is a sort of a scaled down version of the upper ocean steric sea level, which might suggest that there's also something going wrong with the way that we treat Argo floats and make maps of their how we use the individual profiles to make global maps. So this is all still a bit enigmatic to us. We're still actively looking for possible solutions. It's probably not just one of the measurement systems that is to blame. It's probably a combination of many individual problems that work out to a non-closing global sea level budget. So as a takeaway, like since 2015, we don't really close the global sea level budget. Like we have like a part of sea level rise that we measure with altimetry that we cannot explain from barostatic sea level or thermosteric expansion, but we don't really have a smoking gun on which measurement system is suspected. But there is a possibility if we say that this problem is due to hydrographic observations underestimating ocean heat uptake, that the Earth energy imbalance is slightly larger than it is today. But hopefully soon we can find out what is going on here and update all these numbers and solve this little mismatch. And from that, I'm quickly peek into the future, into the very near future. And this is actually pretty actual. Like this is a picture of Annapolis that's close to Washington, DC, which had serious tidal floods this weekend. And we had with the NASA Sea Level Change Science Team 2 years ago, we had our annual meeting in this town. And I think we actually had dinner in this blue building here. And to see that building is now flooded is a bit sad. But we might be able to help these flooding communities by at least giving some accurate predictions of these floodings ahead of time. So that is something that we're going to have a look at. So coastal flooding is like something that's massively on the rise, especially here in the US East Coast and the Gulf Coast, where some places during every spring tide they already see coastal floods. And on top of that, you have storm surges, but they are very difficult to predict very far ahead because they're like individual storm events. But actually, like that, more and more of the floods, they are not driven by these storm events, but just by what's called like sunny day flooding or high tide flooding, by just like very common situations. So it might be if we have information on the background longer term sea level variations on seasonal timescales, we can assess the risk of flooding, that there's like specific months or seasons that sea level, that there's like a higher chance of flooding. And because like when mean sea level is higher, the same tide will cause a higher high tide. So that immediately works out into to a change in the flood risk. And there's here at JPL, we work together with NOAA to advance these seasonal sea level predictions in the RISE project. And one of our pilot locations is the city of Charleston in South Carolina. And here you see a map of flood zones in Charleston, where you can see that a significant amount of the city is in a flood zone. And Charleston is on the Atlantic Ocean, and the Atlantic Ocean is always challenging for sea level predictions on shorter timescales, because, like, for example, in the Pacific, their sea levels often very much driven by El Nino variability, which we, to a certain extent, we can predict a few months ahead, but for the North Atlantic, such a clear indicator is missing. And there's another difficult issue. So how do we often make these seasonal predictions? Is that we start with a coupled climate model, and that's initialized with the present day initial conditions, and then it's run forward. And here you see an example here. This is the CCSM model, CCM4, that's run by Ben Kurtman at the University of Miami and NOAA, and that's initialized. And because because when you initialize this model, then the initial conditions which you prescribe your model, which you have from observations, might not align very well with the model equilibrium, for example, like the Gulf Stream position, for example. So it means that if you start running this model, you get an initialization shock. And that is especially a problem in sea level, because it's like an ocean variable. So changes in the dynamic topography of sea level, they will immediately affect. And that is also happening in the case for Charleston, which is really affected by the location of the Gulf Stream. So if we, every time this CCSM model is initialized, that's the dot, and then it's run forward, sea level immediately drops almost a meter every year, almost every year. There's some here it changed a little bit, but as you can see, this is not very useful for prediction. This is just a wrong prediction. But what might be the case is that the atmospheric forcing that actually drives sea level, so wind stress, heat fluxes, freshwater fluxes, that these atmospheric forcings, that they are accurately predicted, but it's just a problem in the initialization of the ocean model that causes these problems. So we might be able to use this the atmospheric forcing of these prediction models to predict sea level, but we cannot just rely on their ocean model because of these initialization problems. So we came up with a trick.
Thomas, could I interrupt you for a second? Sorry. Yeah. Sorry. We've got a question in the chat from Vivian. I think it was from a slide back. Vivian, would you like to unmute and ask a question? Might be now.
Oh, yes, you were referring to an emergent glacier, a sea level imbalance, from the various measurements. So I was wondering, for the first part of the question would be, you were using the barostatic estimate mainly from GRACE, and how would that compare with independent observations of ice mass losses on glaciers and ice sheets?
Yeah.
And
so Oh yeah, go ahead. So if you then go back here, so that's a very good question, and that is something of the lucky thing with GRACE. Right? So GRACE is like mass conserving, so you can really see like what goes into the ocean must come from land. So and there are a lot of independent measurements, especially from the glaciers and the ice sheets, for example, from the recent ICET2, because there was once like a worry that you see here there's a little gap here, and that's because like that's where you switch from GRACE to GRACE follow-on, so that that should not cause any problems, but you never know. But so if you compare like the ice sheet mass loss with ICET2, also for the input-output method and another satellite altimetry, for example, from the INDI project, it all matches very well. Like there is no for the glaciers and ice sheets, like the numbers, they, if anything, GRACE overestimates them rather than underestimates them. But the tricky thing, what might play a role here is hydrology. And so on interannual scales, for example, during like a peak, like this drop here, you can see like this La Nina drop. This is during La Nina. That's caused by a change in land hydrology. It's like a lot of precipitation caused this drop. Precipitation over South America and Australia caused this drop during La Nina, and that is more difficult to constrain. Although we have some models, especially like sort of more like data-driven models to estimate changes in hydrography, but they don't really show any weird things over this period. So it doesn't look like that GRACE is off That's not like the first, and the number is big, right? If you talk about like since 2015, like to blame Grace, we need like for the last 5 years, we need to have like another Greenland in the sense of mass loss to explain this this discrepancy.
Oh, and the second part of the question was, is there a greater discrepancy if you're looking at the steric components, you know, the various types of measurement that you were discussing? Is that creating a greater discrepancy in the sea level budget?
Do you mean like Argo versus like XPTs or CTDs?
Yeah, right.
We haven't it's into that because like most measurements are Argo nowadays. So, but that might be good. Like it's mostly we compared like multiple like gridded estimates, both with only Argo and Argo as well as CTDs and XPTs, and they all mutually agree very well. But I haven't looked into like a product that does not use Argo. It might be interesting because it might be. Because we know that there's like there have been some problems with salinity in Argo over the last few years. So we correct for that. Does this answer your question?
Pretty much. Thanks.
Yeah, thank you. Let's go further. Here was So then we go back to the ECCO trick. So what ECCO is an ocean state estimate that we run here at JPL as well as at MIT and in the University of Texas in Austin, and it has what's called adjoint capabilities, and that is a very fancy term for if you see like an ocean model as a whole set of differential equations with initial conditions and boundary conditions, that we compute the sensitivity of like any output of the ocean model, the sensitivity to one of the initial or boundary conditions, and that gives what's called adjoint sensitivity maps. So how does that work in practice? That's what you can see here. So this is here it sees like a map of sea level in Charleston and how sensitive that is to changes in the freshwater flux, like the evaporation, precipitation, and runoff. And as you can see here, that and at specific time lag. So you can see here that when there's like a negative freshwater flux anomaly here, then 4 months later, sea level in Charleston will go up. And there's like really like very causal relation to the model equations, not just correlation. And you can see to do that for all these processes, and you can go further back in time. And then you can see like a lot of physical processes that appear from this kind of thing. So you can really see that for the heat flux and the freshwater flux, these anomalies, they are really like transported with the current. So the heat flux and freshwater flux, they change like the upper ocean water density, and these anomalous density waters, they are just affected from like 12 months to 9 months to 4 months towards Charleston, where you can see that for example, the wind stress with this diagonal lines, that's really tricks like of Rossby waves, that wind stress anomalies, they cause change in the thermocline, and these changes, they will propagate as Rossby waves slowly towards the coast. Well, very short time scales, like local winds, they dominate sea level. But if we combine these sensitivities to atmospheric forcing with the atmospheric forcing itself from the prediction model, we can make a sea level prediction. And there's another nice feature of this, is that, for example, if we want to predict sea level 4 months from now, for sensitivities that are already longer than our prediction horizon, we can use observations. So for example, if we have observed a lot of precipitation here, then we know that 8 months later sea level rise in Charleston will change. So we can use both observations and forcing predictions to forecast, to predict sea level rise. And it's really like a delayed, that goes to sea level as a delayed response to open ocean forcing. So we have done that. We have used observations, and we use CCS for predictions. And here you can see our typical prediction in things. So in black is the tide gauge observation. In blue is what ECCO tells us, like the ECCO model output of sea level, and in orange is our like more like a hindguessed prediction type. And you can see that some of the events here, they are pretty well got, while some others are not. So it's a bit of a, at this stage, we're still a little bit of a hit or miss situation. But compared to the original predictions from these coupled climate models, we're already doing much better, or at least like at the right order of magnitude. We have catch some events. So this looks, in a sense, already promising, especially when you look into the quality of our reconstruction. And so we can like assess how well we do this. So we can look to the root mean square error with respect to observations, and we can look into the correlation between the anomalies with respect to the mean seasonal cycle versus observations and predictions. And here you see like the root mean square error with relative after initialization. So if we like predict like 2 months ahead, we make this error, and then we just go back. So you can see that the root mean square error for like the first few months, we seriously do a better job than the mean seasonal cycle in predicting sea level. I haven't shown it here, but if you compare it to like coupled models, they are way off. They do worse than the seasonal cycle in predicting, so they are not useful for predictions. And the same goes here for the anomaly correlation coefficients, which is up to like 6 months or so ahead. Pretty reasonable. It's not very high in the sense that we can accurately get every feature of sea level, but there is definitely predictability of the system. And we can also look into what is causing this predictability, right? Is it because we have these two mechanisms, right? We might be able to predict the forcing, like for short lead times, where we use the CCM model to predict wind stress, to predict freshwater fluxes, etc. And we have this delayed response to of open ocean forcing, that we can use the observations of this forcing and then see, okay, a few months later, sea level will change that way. And we can separate them out with an experiment where we only use the sensitivities towards observed forcing to separate them. And then you can see what's interesting here, that on very short timescales, it's really like the forcing, the predicting of the forcing that really makes the forecast better. But on like longer timescales, like the predictability of sea level in Charleston up to like a few months ahead of time is predicted by this delayed response to open ocean forcing. As you see that both these mechanisms, right, this short-term response to predicted forcing as well as slow response to observed forcing, they both provide mechanisms of predictability. With the longer the time scale, the more important this delayed response to predictability will be. This is still like work in progress. We still like are not yet at a point that it is immediately operational, but we're still working and looking into different models to see whether we can further improve on this. So hopefully soon more on that. And that brings me to the end of today's presentation, and with just some quick take-home messages, right? Remember from the beginning, global sea level is really rising because of the heat that accumulates in the Earth system, and that causes the water to expand, and it melts the ice. But it's really like sea level is, in a sense, a very regional phenomenon. It varies a lot from place to place, and still understanding all these regional processes, that's still work in progress, but we're slowly adding puzzle pieces to this puzzle one by one. So hopefully we will in the future have like a much better grasp on like all that's causing all these regional variations. One of these puzzle pieces used to be is like using tide gauge data rescue and paleo proxies to increase the number of observations that we have, number of observational records. For example, for the South Atlantic Ocean, where we don't have many observations, this can really help us understand what happens in that regions. But even now with satellites, we still have some ongoing problems. We are missing sea level. We still don't fully understand what's causing sea level rise over the last 5 years. And finally, with all this knowledge, with what's causing sea level rise, we might also be able to make like seasonal predictions of coastal sea level, which can really help, hopefully help, especially when these predictions get better over time, to really prepare for flood risks a few months ahead of time. And with this, I'd like to thank you, and please let me know if there's any questions.
Thanks ever so much. Thanks again, Thomas. That was a fascinating talk. We've got a couple of questions, so I'm going to go first to suggest that I believe Sonka in the chat. If you would like to unmute, it'd be fantastic. And then I see Christopher has his hand up.
Hey, Thomas, great talk. Thanks for that. So I just have a simple question. Are you including the long-term trend in your predictions for the Charleston example?
Yeah, that's a good question. That's interesting. So if you go to this picture, so we removed the global mean sea level trend. But what the nice thing is, what sees that in Charleston sea level is rising slightly faster than the global mean, and that feature is reproduced by our prediction. So we see that like the increase in heat content change is and the changes in the wind patterns, they drive long-term effects, and we're able to predict that.
Okay, so I mean, you're using the tide gauge. I guess there will be also residual vertical land motion trend or something. So have you tested whether the statistics actually improve when you include that kind of residual trend?
Yeah, so we also checked it with satellite altimetry, which should not be affected that much by land motion. It gives more or less the same results.
Okay.
I think like it's mostly driven by like high frequency variations. That's really like driving the variations here, and also the scale. But yeah, it's definitely something we have to keep in mind, that vertical land motion plays a role here as well, especially like in the US Southeast.
Okay, thank you.
Thanks, guys. Chris, would you like to unmute?
Yeah, sure. Thanks, Craig. Thomas, thank you very much. Really multifaceted talk. I really appreciated it. I'm really fascinated by the work that you've done with your colleagues in the South Atlantic. So I have a question related to that. So part of what motivates your work is this earlier paper by Phil Thompson and Mark Merrifield about almost a decade ago now, where they use altimetry over 2 decades to argue that on those timescales you get coherent variation over that region. And a lot of, and kind of much to Phil's chagrin, you know, a lot of papers have picked up on those regions and assumed that spatial covariance structure is applicable over much longer timescales. This is the region you showed, that right there, that region you showed in your slide there.
This one.
Yeah, so that green region there. I'm wondering, as you and your colleagues have sort of worked to improve data availability, both rescuing archival records like from Dakar, but also bringing in paleo proxy records, I'm wondering if you can sort of go beyond the assumption that a lot of past studies have made, which is just to take the Thompson and Merrifield regions and rather test essentially make a test of their region. In other words, you have more and more data from the South Atlantic region, and I'm wondering, my question is, are you at a point, is there enough data in the South Atlantic that one can actually make a test of the Thompson and Merrifield regions to see whether or not, as a function, say, of timescale, that big green region is really valid, and whether people who are, say, reconstructing global mean sea level over the past century should be doing sort of, you know, a box average of tide gauge records over that region?
That's a very good question. Yeah, that's a tricky one, because if you look into the records, then you see the problem that pops up, and that is here. So here you can see like all these records, and you can see like there's a lot of variability in some of these records, for example, in Buenos Aires. And it's already super tricky to find out like which part of like this Buenos Aires record, for example, is like driven by like local effects, right? For example, it's located in the estuary. So how far is this not a river gauge?
Yeah, well, I mean, people have made a real point. I mean, just to interrupt you, I mean, it's this slide that made me ask my question, because I mean, Buenos Aires in particular, you get that huge jump in the early 80s, which people have sort of attributed to sort of really strong precipitation during the 82, 83 El Nino. That really increased river flow through that estuary, created this big sediment load. That big increase in the early 80s could be this sort of episodic type of vertical land motion type event, right?
Yeah, exactly. So that's definitely a problem that we see. Like we only have this very limited number of records. So the question is like, what do all these peaks represent? Like, is it like a local signal, or like which part is driven by like larger scale ocean dynamics that we reflected in a pattern like what Phil Thompson and Mark Merfield have found? So that is a very big question. It's like, and you see like, for example, in the Falkland Islands, where you only have like 15 index points or something, like you cannot really say a lot about it. So I think it's an assumption that is maybe not the strongest assumption ever, but like, what is the alternative? It's a bit
yeah, it might be something to think. Yeah, I mean, essentially the worry is whether this is sort of a big systematic structural error that's lurking in a lot of recent reconstructions that are based on. But anyway, yeah, no, I realize the reality of the data, but just sort of a thought, what we would need in order to test that result.
Yeah, it's tricky. It's it might work like that. That is what I think would be really nice. We can like really separate like this Buenos Aires record into like what is causing this, what's causing all these peaks. Like, can we attribute it to like river discharge? Can we attribute it to like local wind effects, local storm surges? Really like disentangling all these records themselves, see what these records themselves tell us. I think that is something we really have to work, because now because we don't know that, we have to like throw them all on the heap.
Yeah. All right, great. Well, thanks very much.
Thanks, guys. Are there any further questions? Do we have any extra questions? I'm not hearing it. Maybe someone is stumbling to unmute. We're a little bit over time here. People are sort of like starting to filter out. I have a perhaps less technical question, kind of dumb question, if you would. So you mentioned earlier something along the lines. Oh, there's something from Ian. I'll let Ian go. I'm sure it's more interesting.
Yeah, thanks. I guess I'll take the opportunity. Thomas, thank you for the talk. That was insightful. I'm curious the degree to which, I guess, how much confidence you assign to sort of the underlying GIA model in terms of that half-meter variation that you're trying to explain. I mean, I guess it's time varying, so that doesn't explain it, but I'd be curious about your response to that first question, just in general.
So like, you mean for South Africa, for South Atlantic, or for the?
Well, I guess this area in particular, since you've got the slide up, but I'd be interested about because you're noting that it's corrected. You're using that to correct.
Yeah. Oh yeah.
Effects, right?
Yeah. This picture. Yeah.
Yeah.
Talk about this 0.5 millimeter per year. Yeah. How certain is that? Yeah, that's a good question, because it depends on two factors, right? As the first one is like these GIA models. They are constructed by having an estimate of like the ice sheet history, like how have all the ice sheets melted since the last glacial maximum, and the solid earth rheology, like how does the solid earth react to changes in how fast the ice loads the earth. And this is a mean plot, but luckily a colleague of mine, Lambert Carol, he did a very big experiment where he varied all these parameters a lot, like really to really extreme values that are way out. So we have, and from that you could benchmark all their these GIA models to observations. So there you get like a reasonable constraint of this number. So we can put an uncertainty on this number, and I think that this is 0.5, but I think the uncertainty here would be like on the level of like 0.1, 0.2 by just varying all these parameters. So this 0.5 or something might not be exact, but it's definitely pointing into the right direction. So we're like pretty sure like we don't know exactly like the exact features of this pattern, but the general shape of this pattern is, I think, very well established. Like,
Thanks, Ian. Okie doke. We are now about 10 minutes past. We should probably close off soon. Do we have any final questions for anyone? Speak now, forever hold, please. Okie doke. Yeah, we should probably close off. But thank you ever so much, Thomas, again for a fascinating talk. It was both really nice for the series and really neat. And yeah, hopefully we'll see you again perhaps in 6 months' time. And I'll beg you again to give a talk. If you have anything new, let me know.
Yep.
If you can think of anyone who would like to speak in the series, please let me know. Okay, thanks everyone for joining us. I hope you have a great rest of the day. Everyone has left.
Now you can finally ask your question.